Okay, let's get into chapter 4, the Internet Protocol layer. And for sure, this is the most important layer of the protocol stack because it's implemented in every node that need to participate in the internet. So every node need to have an IP address. So if a node has IP address, it would have the IP layer. So that's the essential layer. As we say that the protocol stack is more like an hourglass, that you have only one protocol in the middle, that's IP, but you have many in the link layer and physical layer, and you have huge number of application layer on the top. So the core, in the middle you have only IP, and in the transport layer you have only TCP and UDP or plus RTP. So it's quite limited. The core, the in the middle layer is quite limited. So we'll look at the general issue as first, as the other chapter. There'll be general issues, and then we look at the data plane protocol, which are IPv4 and IPv6. So right now we are mostly using v4, but there are more packets which are in IPv6. Say on NCTU, there is a IPv6 beta site that have IPv6 client or servers. So we have the switch and router on a campus need to handle both IPv4 packet and also IPv6 packet. So we look at these two. However, there are some other control plane protocols. So we break down the control plane protocol into 4 categories. The first one is address management, and here we will see ARP, address resolution protocol, and RARP, which is reverse ARP, and also we would have DHCP, dynamic host configuration protocol, which would issue IP addresses and some other parameters to the client. So here we will see ARP, RARP, and DHCP for address management. And then error reporting is another control plane protocol by ICMP, Internet Control Message Protocol, which is for error reporting. If there is something wrong on the network, on any node, the node would send ICMP message to the source of the packet. If there's an error when handling a packet, we will send an ICMP message to the source of the packet to notify, okay, you send a packet and this packet is now in trouble. Okay, and that's done by ICMP. And then the next two will be on routing. One is for unicast routing, which we didn't specify unicast here. So if we didn't specify, we just say routing, it means unicast routing. And then there's another category for multicast routing, that it in a sense that it needs to it would expect the router to do multicasting. So I probably want to send a packet to 10 hosts. However, instead of sending 10 packets to the host, to the 10 hosts, I want to send just one packet to the router. and then hopefully the router would duplicate a packet to the 10 host. So for the sender, for the source, it would just send 1 packet instead of 10. So it's the multicasting is done by the routers instead of by the source. Okay, so but for that to happen, it would change the router behavior a lot, and in fact, it would change the stateless router into stateful routers. So we will see that IP multicast does not succeed. In a sense, it does not succeed. It only gets deployed on a very limited scale, especially on a local area. For example, you can do multicasting on the campus on only the LAN, but not on the internet. Meaning that all your multicast recipients, all the receivers of multicast are on the same network, on the same LAN, instead of across the internet in a wide area. The reason is because if we implement IP multicast globally, it would turn the router from stateless to stateful. That would destroy the stateless nature of IP routers. So instead of IP multicasting, application multicasting is more popular. Where in application multicasting, the multicasting is done by the servers, the multicast servers, instead of by routers. And there's a sidebar in this chapter talking about the application multicast versus IP multicast. There's a sidebar on that. So multicast routing is not successfully deployed well. It's only deployed in a limited scale in the local area. Okay. And you would ask, where are we going to talk about the packet forwarding? Well, we'll talk about the packet routing in section 4.6 and 4.7. These are the control plane protocol that would do the calculation. It would calculate the path. But the data plane operation is in section 4.2. So the table lookup, when you forward a packet, you actually do the table lookup to do longest prefix matching, which we will see pretty soon. And that table lookup is actually that you need to in order to forward a packet. But to calculate the path in the background, it's the control plane's job. So again, I'd like to remind you in what we cover in chapter 1 about the difference between control plane and data plane. And forwarding is data plane, and routing is control plane. And routing does calculation, say Bellman-4 algorithm or Dijkstra algorithm. Okay. So don't misconfuse these two. But again, in this society, people mention routing even when they are talking about forwarding. So they might use routing for both data plane forwarding and also for control plane calculation. They will use the same term, routing. But it's better not to use the same term. It's better to differentiate them. Okay. Okay, here's we put the protocol we would discuss in this chapter. Most, not every. Okay, so here you see on the left-hand side, there's a host machine, and it's connected to the internet through two things. One is NAT server, NAT device, and then to router. Okay, And the reason why it has an NAT device in the middle, NAT server or NAT device in the middle, is because it probably use a private IP address for the host. So we'll talk about private IP address in section 4.2 when we talk about IP protocol. And so the NAT device will need to do the mapping, translation from private IP address to public IP address, and vice versa. Okay. And on the host, you see it would implement application layer, and also the transport layer, and then IP layer, and there's a companion protocol, ICMP, a control protocol, and also ARP, another control protocol. And within the host, there should be some configuration from DHCP server. The DHCP server will give the IP address and the subnet mask, subnet address and subnet mask, and then the default router to the host. So the host get this configuration from the DHCP server. And the reason why it need the IP address and subnet and default router is because first of all, I need IP address. Even if it's a private IP address, I still need an address. Okay, and then a subnet. I need to know the subnet mask so that I know which part of the address within the 32 bits, which we will see, the 32-bit IP address within this. What is the network address? What is the host number? So you usually break down into two parts, the network address and the host number. And we need to know what is the network address and what is the host number. And then a default router, I need to know if I'm going to send a packet to a host which is not in the same subnet, not within the same broadcast domain, then I need to send the packet to the default router. So everything, if a destination host is not in the same subnet or not in the same broadcast domain, then I send a packet to the default router, because then default router will will forward the packet to the destination. So I need to know who is the default router or the address of the default router. And if I know the default router, the IP address of the default router, and I want to send a packet to the default router, I still need to know not just the IP address of the default router, but I also need to know the MAC address of the default router. So how do I know the MAC address of the default router? Given I have known the IP address of the default router, I know the IP address of the default router from the DHCP server. But how do I translate the IP address of the default router to the MAC address of the default router? How? Then I need to use ARP, Address Resolution Protocol. Okay. With ARP, I can broadcast on the subnet or the broadcast domain. I can broadcast to ask who has this IP address. I would ask who have this IP address, and the station who has this IP address would then would send an ARP reply, which is unicast, an unicast reply, telling me, okay, I have the IP address, and here's my MAC address. Okay, so by ARP request and response, the request is broadcast and the response unicast, we wouldn't be able to map the IP address to the MAC address. So with the MAC address, then I can happily fill up the frame, not just the IP address, the IP packet, and then the frame header. I need to fill in within the frame header the destination MAC address. So I know that, I fill in and I send the frame. And when I send a frame, it will be destined to that particular router, the default router. So that's the purpose of ARP. Not just to default router. If I want to send a frame to another host on the same subnet, then I would do the same. I have the IP address of that destination, which is on the same subnet as I. Then I still need to translate the IP address to the MAC address. And the way I do that is send ARP request, broadcast request, broadcast the ARP request. And how do I send a broadcast frame? If I want to send an ARP, but I need to broadcast this ARP, how do I send a frame that will broadcast to the other station on the same subnet or broadcast domain? How? In chapter 3, we know that, right? 01, yeah. The destination MAC address should be 01s, right? Then the switch will know, okay, this is a broadcast frame, and it should be duplicated to all the other ports. Okay, so that's ARP. And then you will see that in an NAT device, the NAT module needs to do the address translation. It needs to translate the IP address, probably even the port number in the TCP or UDP port number. So you would translate the IP address and the port number in the transport layer, the IP address in the network layer. And those kind of translation sometimes get very messy. The reason is because you probably not just translate the address or port number within the IP header and the transport header, TCP header or UDP header. You probably need to also translate the IP address or port number within the application messages. That's because some application protocols, they have put IP address and port number in the application messages. And we will see that in chapter 6, that many applications do that. But there are some examples here in this chapter that you will see in FTP, they have done that. In FTP messages, you will see port number. And if the NAT translates the port number in the network layer, it would need to get into the application message, FTP message, to change that port number in order to be consistent. So doing that translation is kind of messy. And that's due to the cross-layer issues. The application layer have used network or transport layer information in the message, in the application message. Then there will be layer interdependency. When we design the protocol layers, they are supposed to be independent from each other. But unfortunately, when people are designing applications, protocols, they do not completely obey, do not completely follow the spirit of interdependency. They have dependency when they put IP address and port number in the application messages. They are not supposed to do that. It's bad to do that, but they did it. And many applications did it. Okay. So then NAT become very messy, as we will see. And when you design and implement a product of NAT with NAT features, you would spend a lot of time handling these kind of translations. Okay, and we will see that. And the router, it has the forwarding here within the data plane, the table lookup, but it need to look up the table But the table, routing table is not, it's actually calculated. The computation is done in the background by the routing protocols. So there'll be a set of protocols here that does the calculation. And the most common protocol, unicast routing protocol, are RIP, OSPF, and BGP. And we will see the difference between them and where they are used. Okay, the first open source implementation in this chapter is the IP layer packet flows in code graphs. So you see two directions. One is the incoming, the receive, on the left-hand side, and the right-hand side is the transmit. On the left-hand side, the receiving part, you have seen this function, these two functions. We have seen that in chapter 3, in the driver. The driver will call the IP layer. Within the driver, it will call the IP layer. And IP layer is a sequence of function call. And here it would call the transport layer. However, it would have several transport layers to call. Either if the transport layer is either TCP or UDP or row, meaning no transport layer, directly to the upper layer. So row, UDP, or TCP. Here, for the outgoing, it would, again, three modules that would call the function here. It will be row, UDP, and TCP. They will call from different functions. They will call these functions in order to transmit the packet. And then here, this function will call the drivers. We have seen this too in the driver. So it will call, this function will call this too in order to transmit the packet into frames.